Hi everyone, welcome to the 10th edition of Campus to Corporate webinar. 10th webinar, sorry, not 10th session of the webinar. I'm sorry, I went to wrong PPT. I'm sorry about it. Just give me a minute. Some issues with the sharing. Wow, why am I not able to share? I'm not able to share for some reason.
Shankar has to stop sharing.
No, I shared. I stopped it. Oh man. No, who I don't know. Share screen is not coming to me. Unfortunate. I got the screen, but I had a wrong PPT. It doesn't work. Let me refresh. Maybe get out.
Yeah.
What should I do? Should I just talk over the slides then?
No, or send it to me. I'll
it's okay. I'll just
send me the slides. Send me the slides.
Let me just email it. Give me a minute. Sorry about it, guys. There's some technical issue.
Just send me the slides in WhatsApp. I can share it here, Hari.
Yeah, I sent it. Just now I sent it by email. Let me try sharing again. No, it doesn't come. Anyway, let me talk. Let's get started. Yeah, so welcome you all to the webinar series. This is the 10th webinar of the 12 webinar series. Right, and this is the Organite team. This is myself, Hari Seshadri, and we have Madhubala from the org team present here. Hi, Madhu.
Hi, everyone.
And this is an webinar is in joint partnership with IEEE Blended Learning Program and with Sevalaya, the NGO. Right. So this is a partnering team, and we are very thankful to our sponsors and partners. Getting to Goal Professionally, Mentor Card, AirMeet. Thanks for the wonderful platform what you're using now. Seer Academy and Triple IT DM Kanchipuram. And we also want to thank our donors for contributing supporting the Sevalaya and the institution. They are the institutions with Chennai Institute of Technology, Sri Venkateswara College of Engineering, Bellwether Advisors, Spiker Works, and Rap Chips. They are institutions corporate who are donated to Sevalaya. They are our donors. And we also want to some of the donors who are agreed to display their names, but it's not a full list. Although your display is sharing now? No, not yet. Okay, let me just read through the names.
I haven't received it.
Okay, anyway, let me read out the names. Yeah, the names are Hariharan Seshadri, Malik Mahalingam from USA, Tanige Arasu from Singapore, Balaji Venkatesh from USA, and we have a student who has actually donated to the NGO. We would like to thank to Mr. Guda Venkata Kaushik. He's from Sri Venkateswara College of Engineering. It's a noble effort from a student coming and donating to the the NGO. And Mr. Arvind B. Rao, Mr. Srinivasa Rao Kollu from USA, Dr. Anuradha Natarajan, Mr. Arun Biksheswaran from USA, Mr. Sriram Satakopan from USA, Mr. Srikanth Raghavan, and there are a few donors who don't want to disclose our names. And there are a few more, like we are awaiting their permission whether we can take out the name. So it'll become inspiration for others to donate for the noble cause. So we are thank all our volunteers, Mr. Arun Karthik, Mr. Srinivas Ram, who are students from SREC Coimbatore, who helped with a lot of back-end work. And we also thank our webinar creative person who helped from SVH Graphics, and the person who created our social media cover pages and logo, and website designer for the Springbok Technologies, right? And any donations we make, it's a voluntary completely. It goes to Sevalaya NGO for the skill development for the rural youth who are impacted by the COVID, and we'll be posting that information in the chat window as we move forward, right? And I would like to introduce the guest of honor of today, Mr. G. Balasubramaniam, who's a Chief Placement Officer, India and Dubai at BITS Pilani. He's been that role for last 7 years, and yeah, he's doing various stakeholder management, change management, and he's been doing the role success. He's managing a team, and he's adding a lot of value to the stakeholders, and he's been doing a phenomenal job at BITS Pilani, the complete all the campuses, including Dubai. Right? Welcome you, sir. And so he was in the past, prior to the 2003 joining BITS Pilani, and he was a CEO of the Paradigm Consulting, He was supporting by hiring and consulting kind of companies. And prior to that, he was at HCL Infosystems and with Canon Sales Executive, and he has an MBA from Xavier Institute of Management. Welcome you, sir.
Thanks, Hari. Thanks, Madhu.
Yeah. So,
Good evening, everybody.
yeah,
Good
we can
evening,
hear you.
everyone.
Yeah, we can hear you, sir. You can go
Yep.
ahead.
Thank you. Wishing everybody very fast recovery from the COVID blues, and wishing everybody uh, a faster return to normalcy in Unlock 5.0. Now, with today's series, we have Mr. Shankaranarayan Bhat. I take this opportunity to extend a very warm welcome to Mr. Shankaranarayan Bhat. It's an honor as well as a privilege to introduce a very well entrenched and an accomplished professional like Mr. Shankaranarayan Bhat. Very rarely we come across a resume which has only 3 organizations. Shankar, if I may call him so, has only 3 organizations to his credit, which is a very rarity in today's circumstances. Normally, uh, for a 2 decade plus work experience, you have more than 10 to 12 organizations. So that says volumes about people like Shankar. So to give a brief intro about Shankar, Shankar comes with about 20 plus years of experience in VLSI industry. His expertise is in SoC design, DFT, pre-silicon verification, and post-silicon validation. His he is a B Electronics and Communication from SDM College of Engineering, Dharwad, and he has 3 patents to his credit. He has worked on more than 50 SoC designs, and he has worked with 3 organizations. His current role is as a director of engineering with Intel Corporation, and his past experience is with Qualcomm as director of engineering, and he was with Wipro as a project manager. So 20 plus years, three organizations, 3 stints. Welcome you, Shankar.
So, yeah, thank you, Balasubramanian sir. It was a very wonderful, nice. Thanks a lot for introducing me. Let me know if you guys are able to hear me.
Yeah, we can. Yeah.
Okay, so I'm just sharing my screen. So first of all, I would like to thank the Springbok Technologies and Sevalaya for such a wonderful initiative. This, I think, is like my honor to be here today, sharing my experiences and some of the like learnings what I got. Right, and also to be part of the Basudhanim sir in the sharing the stage. So let me get started. I'm going to talk about. I think you guys have been going through the various parts of the VLSI design and the validation and the VLSI industry, how it is. I think it's a very tough time of COVID situation, and the key thing is like you possessing a right skill is actually going to help you to the get your job faster. Right. So, and I'll be walking you through. You would have already gone through the. I saw in the past sessions you went through design, you went through physical design, the DFT, all of that, and I'll be walking you through what happens after the silicon is manufactured, like the post silicon testing and qualification. So first thing is like all the information in this document which I'm sharing or which I'm going to speak during the next 1 hour is my learnings and experiences. It does not belong to the any industry or any organization, not to the Intel or any organization. It's my personal views, but pretty much all the industry works on the same basic concept. Okay. I'm going to skip. Let me start with yes, one nice quote. The Andrew Grove, who is one of the founder of Intel, which I always admire is many of these quotes. Right, the corporation is a living organism. I think you can read the thing uh, on the screen, and what it means is there is no fixed textbook. When you are doing an engineering, you still have a textbook. May not be one. There are multiple textbooks. There are multiple syllabus. At least there is a defined syllabus which you have to study, you have to work, you have to read, you have to deliver an exam. But when it comes to corporations, there is nothing like a fixed boundary, and the strategy or the learning or even the delivery has to change, adapt time to time, and the change is the only constant, and you have to adapt to new technology, and you have to learn the new domains, new skills. So it's a constant change which happens in the corporation, right? And the key is like, you should be willing to change, and you should also be like, learning new domains and being excited, right? In my personal career, I have changed my domain 3 times, totally orthogonal once though. Like I did a post silicon testing for 7 years, then I moved into the pre-silicon world, then I designed for test DFT for another 7 years, and then I went into validation. And all the skill set needed in each of those domains were very different. So that's where the corporation is like, there will be continuous change, and you have to keep adapting yourself, right? Let me start with few tips of my career. All of you are uh, just completing your degree or completed your engineering or a post graduation degree. So being in a good scoring good, in the college, I wanted to work on a VLSI design, right? And pretty much everyone thinks about VLSI design, and when it comes, all people know is a design or architecture. And when I joined the industry, it was in a 2000, towards the end of 2000, and probably in the 2001, when there was a slowdown in the economical slowdown. I think it was very much similar to the COVID situation today, where we have like where the job market is little low, people are like cautious, companies are working from home, and all kind of various things. So it was economical slowdown. So I didn't have a choice. I was put on a testing, right? I started doing a test pattern generations, right? And my journey continues on the testing, and which probably for the first 1 month I was not really happy with that. I went to my manager and told I wanted to be in design, I want to do design. But he said, okay, you do this, do good, and then we'll give a change in next 6 months to an year, right? And in that 6 month, what I learned and what I started delivering, I never asked for a change. I just continued on the same domain and started expanding my horizons in that domain. And I've been leading a teams like, I'm leading a teams for more than 200 people team in the last 7-8 years. I've been a director in Qualcomm, and presently also I'm leading a team in IoTG in Intel. So all I can tell you is like, people keep telling I keep hearing the new college grads coming and telling I want to be in design, I want to learn this. There's no boundary for learning, and wherever you are, whichever domain you are, you can always learn and you can always build. And what makes difference is the domain expertise which you have, and the engineering thinking, and your architecture knowledge. So rest all is a tool and flow which you use, right? Your debugger skills, architecture knowledge, that makes a difference, and for that you don't really have to be in a particular domain. And many a times taking a career path which is less traveled, say testing in India today may not be so many people explored it. And I found huge opportunity in that area where I could do some innovations. And I filed around 7 patents, and 3 of them approved, and the 4 are in still in with the patent committee, right? And that kind of opportunity I got because working in a testing, right? So my tip is like, maybe as an engineer, when you come out of the campus to any corporation organization, you may not get a choice that which team are going to join and work. But whichever team you join, focus, learn something, deliver, and which will build your career. Tips on my career too, right? Like my second tip, I keep hearing I don't have time and too much of work, and I happened to join this company. Like I joined this company like few years back, right? My second job is Qualcomm. People told me that like, oh, there's too much of work, you don't want to go. But I worked there 12 years, and I'll tell you what, like, it's all about you, how you manage your life, how you manage your priority, and how you manage your like. So it starts from even at your college days. If you're organized, if you are well planning your task, be it your personal or your career, it will help you to build your career. Okay. And quit saying you don't have time. You have time for what you make time for in your life. So what is in priority in your life, that makes a difference. Okay. So that's my second thing. Now I want to switch to the technical part of it webinar, the VLSI flow. So you have seen this entire thing in the last sessions, right? How the design cycle is, how the design specification is converted into behavioral description, and from there the RTL coding, then test structure insertion, and the verification, synthesis, layout verification, physical implementation, floor planning, netlist, all of that. So this is a complete design cycle flow from specification to the GDS2, right? I'm not going to talk about this part of it because this is something you guys would have already covered it. I'm going to talk more on what happens after your layout is shipped to the fab, right? So the what is the post silicon part of it? So once your layout is shipped to the fab, let me just okay. So once your layout is shipped to the fab, it goes for manufacturing, and I will cover a little more details on the manufacturing. A wafer is gets manufactured, and based on the technology and the manufacturing houses, like say Intel is one of the fab, so Intel manufactures our own chips. Then you have a TSMC or Samsung, the various foundries who manufacture their wafers from silicon. And once silicon is manufacturing wafer happens, the first part is a wafer sort testing. So the you need to prune out when you manufacture a wafer, you need to prune out whichever the bad ones and then go for the good ones. So wafer sort testing happens, and to do a wafer sort testing you need an hardware, which is a tester hardware, which could be SIU, which is a sort wafer sort uh, design unit, right? So SIU. So that's the one which you will go and interface each of the wafers and each die. And then you will also have, once you have the wafer coming, you need to have the patterns. I will cover more details on the patterns in the subsequent slides. And these test patterns, which are generated out of a netlist, are applied to the wafer sort testing. And the good dies, each SoC or each unit of a wafer is called as a die, and a good die goes for the packaging. So the package will consist of like all the plastic material or whatever the material which is used, IOs coming out, and you will have a heat sink capabilities, all of them, and electrical ESD, all those parameters. And the good dies, working die, will go for a package. And the package parts, once you package the parts, again you need to do a testing on the package parts to make sure that your package parts are good, they can be shipped. And the key thing is like when you're doing both of this wafer sort testing and package testing, your goal is to test and screen out manufacturing defects. Your design is already validated by the logic functional verification, logical verification, and the layout verification. So in this stage your intention is not to do the design qualification, it is more of a silicon qualification, right? And once you have package parts testing done, the next stage is the qual testing. So you need to ensure the each of the chip which you are shipping out meets a certain quality requirements and meets all the spec which you have. And if you're working in a lab, you have seen all the data sheets and the spec. So all those specs are generated and validated in this qual part of the testing. And after qual testing, you go to burn-in testing. Burn-in is a high temperature operating life or burn-in. I'll cover more details. Is more of a stress testing. And once you have a parts passing on the burn-in and passing all this flow, they will also go into the system validation. Now, from the flow from here, the left side, you are covered how silicon is manufacturing quality is good, it meets a data sheet. But before you ship parts to customer, you also need to validate, make sure that their part SoC meets all functional and performance required. I said like, okay, you've already done the functional verification, layout verification, logical verification, your design is good. But how do you ensure a design, whatever validation you have done, a design performance is matching with the silicon performance? So for that purpose, you still have to do a kind of performance and functional validation and make sure that it meets. And there are various ways of doing it. There are certain organizations doing this system validation on sample parts, and some doing in every part based on the type of application. If your application is a auto or which needs high DPPM, then pretty much every part goes to the system testing. And if you are going on other applications which is not critical on a DPPM, you will be having it like on a sample part, right? And apart from that, you will also have a system validation. This is a functional validation and a performance validation, and also there will be software testing on certain parts, right? So why I've shown these two separate over here, these two, system validation and software testing, is like only sample parts go to this software testing and system validation, and all the manufacturing parts which are going to customer, typically they will go to this aeroflow, right? And once you do all this testing, if your DPPM, and the DPPM is a defective parts per million, so each of the product line based on the product application will have a goal for DPPM. Say now you have uh, an automobile product, like maybe you can have like less than 20 DPPM. That means, like, say if you are shipping 1 million parts, then maybe only less than 20, maybe one or two parts may become a failure, right? And maybe each product will have its own goal. There are products with 500 DPPM. That means if you are shipping 1 million parts, up to 500 parts may have a failure, right? So that's the DPPM part of it. And again, there are different ways to eliminate them further, and once you ship the parts, so with the board testing, all of that. But once you meet your goal on a DPPM, then you will start shipping that part to customer. So what happens if you are not meeting that goal? Then actually you will go back to this entire thing. You will go back to a first sort testing, you will go back to package call, be it a burn-in or system validation. You will go and enhance your test coverage to make sure that you still meet your DPPM goals, right? There are various means of techniques to enhance the quality of the testing. The various measures to calculate the DPPM, how it will be based on the coverage which you have, the DFT coverage and all of that. So this is the overall silicon flow, where from at a very high level, maybe 30,000 feet high level, from the silicon manufacturing to the parts which is physically shipped out of the organization. Okay, so let me start with the silicon manufacturing flow. I'm not going to speak through each and everything over here. So the first thing is you have your layout design. So once your layout design goes to the fab, then there is you would have already studied on the manufacturing fab process, right? So you will create the silicon ingot with this crystal growing, and that is sliced into wafers and polishing, right? And then there will be epitaxial growth of silicon, and the oxidation, the photolithography, and the mask generation. I think probably I would have moved this layout design to somewhere here, because these two happen independent of the silicon, and this is where you will start your actual design data coming in. And you will create the mask, and with the photolithography, and you will etching and the ion implantation, and CVD metal deposition, and eventually you are making a wafer. So each one of these stages which I captured here, I'm not going to cover that in detail, because each of the topic could be hours of discussion. Photolithography can take like several hours of discussion to understand, and then so I would only say I captured at the end what are the skill sets. I would say this 1 hour session will only give you a little bit of orientation and the knowledge about to how the industry, what is happening, what are the skill sets needed, kind of thing. So it's not going to tell you in detail of each of these domain. I would say you can go through some of these books and read and understand this process, which will help to build your career, right? Whether it doesn't matter whether you are in a VLSI design or validation or any domain, you still need to know the silicon manufacturing and the end-to-end flow. You are supposed to know from RTL design or spec to the silicon, right? And until the customer sample goes out, even how it is implemented in the board. So some of this knowledge is very basic, and which I would say, like, irrespective of which domain you're taking, if you are going to be in VLSI and you want to build your career in VLSI, go over some of these documents and then understand each of these uh, each of these stages in detail, right? And then eventually the wafer gets cut after testing and built into the uh, package parts. So this is a silicon manufacturing flow, and I'm switching to the testing. So once you have your silicon is manufactured, the next thing is screening out the manufacturing defects. So what can happen when you are the manufacturing silicon is, like, there could be impurities, there could be contaminations, and many times because of the contaminations, your design, though is perfect, the silicon may come out as a faulty. And it could be faulty, basically it's a stuck at, maybe there is a short, power to ground short on some of the circuit, or it could be a performance derelation, like the instead of working at 500 megahertz, maybe circuit works at only 450. So you need to screen out all these things, which is a manufacturing defects, where design is proven and something went wrong during manufacturing, right, which is called as your defect density. So unless you have a right defect density, you're going to see the manufacturing faults. And also when you have a wafer, it could be 12-inch, it could be 10-inch. When you have a wafer, and based on your die size and the design size, the you may have like 100 SOCs in a wafer, or you may have even 500. Now, out of that, say, assume you have 500 dice on a wafer, your all 500 won't be good. Maybe there is something impurity, and based on defect density, some of the things you will see a failure, and that will purely depends on the defect density. Like, say, and you need to screen that out, and that's why all this testing and silicon qualification is used. And you have to ensure that DPPM goals are met. Like I explained what is the DPPM. So you need to make sure that customer is not going to see any failure at their end, right? So for example, you buy a mobile, as a customer you will never like to see a faulty model in your hand and visiting the customer care for repair. Similar way, every customer will expect the same. And when you go to certain industry, say you are in a autonomous car, or you're working on a ABS chip. I used to work on a automobile auto microcontrollers when I was working for TI, Texas Instruments. So there, the quality, because the chips which I was working, they were actually for the ABS airbag chips and the dashboard. The quality of those chips are very, very high. You cannot even have 20 DPPMs on them, and where the coverage testing is very, very important. So you have to make sure that your goals are met, and you have to make sure that your functionality and performance is met as per the design, and whatever specifications data sheet which is given, you meet those things, your silicon meets all those data sheet. And it's not that, like, when you're, like I said, when you're testing like a million parts, like million or 30 million, 40 million, you have to make sure that, and what may happen is, over a period of time, like, you even assume you are one of the best person, and you're doing a task and repetitively, and you may end up in doing something wrong, right? And similar way, even if you have the best of the best tools and the flow, it's very difficult to make sure the deviation from the mean, or there's no sigma deviation, is not like way apart, right, which in the limit. So you have to make sure that your design is perfect, and it meets all the every part. Say you're having 50 million parts, you have to make sure that every part meets this specification, right? So that's a very bigger challenge, and for that, manufacturing testing is used. And other thing is the software performance optimization along with hardware. So once your hardware is there, there's also a software part of it, and even software needs to be uh, very, very optimized, right? And it cannot take like few minutes to unboot your system, right? So it has to be very, very fast and very optimized and on the performance. So there this testing and qualification also used to fine tune the software optimization and the settings. Let me start with the test hardware design. Right. So there are various type of testers. Like I just put a picture of one of them, which is an Agile 93K tester. But you have various other testers, and when you have a tester, this is the each of the die in a wafer is this is the probe card where the golden needles are going to make that here is going to touch the IO of the wafer on a die. And now you need to design this hardware which will go and make a contact with each of the IO. And when it comes to testing world, the you don't it's not a simulator, or you don't have any means of looking what is happening inside the chip. All you have is only the IOs. So every communication to the your SOC or your design has to happen to peripherals and IOs which you have. So and so you are going to you need to design these probe card. There are two things. One is a probe card, and other one is a uh, TIO, or the package part testing unit. So you need to design this the probe card and the test heads, which will go and make it. These will be like anywhere from 10 to 20, 40, up to 30 layers of a board design, and based on complexity increases based on the type of the chip which you are testing. uh, and this hardware needs to be designed for every chip. Okay. Now there is a second type of hardware which is a board. So if you're like I was telling that you have a system level testing, you have platform testing. For that you need a board which has a FPGA and all the peripherals mounted on it, and where you will put your SoC and do a full FPGA board testing. So there's a other set of board. So this is a other big skill or a big work which happens is all this hardware design, board designs. So and for each of the each of the SoC or each of the devices, there'll be unique boards connected and unique hardware. So this is the other thing, the connecting, right? And so that, like I said, the automated test equipments, ATE tester, probe bus handlers, probe cards, ATE load board sockets, all this design is a one stream of activity which happens. So the next one is, say you have a silicon coming, then you have a board ready. Now your board has made a contact to the die, and you need to test that, right? And to test that, you need a pattern. Now the tester, like I said, does not understand anything inside the chip, or does not have ability to see what happens inside the chip. Like if you're doing I'm sure all of you have done a Verilog VHDL system Verilog simulations, right, with the simulators. So in the simulations you can load your design in the simulator and you can go and exactly see inside the register what happens. But when it comes to a tester, ATE testing, don't have access inside the chip. All you have is only IOs. Through IOs you need to access and understand what's happening inside the chip. So for that you need to create a patterns. And when it comes to patterns, the eventually the tester can understand only binary, right? So and eventually everything goes into an electrical parameter, right? So either it's a voltage applied or voltage compared. So a typical test head has a this basic circuit where it's a test head is a DUT is a device under test, which is your chip. And I have oversimplified this circuit. It's much more complex. So your test head will have a two basic things. One is a signal generator, other one is a comparator. So the signal generator generates a voltage to the test head, and signal generator provides a logic value 0 or 1, for example, which needs to be applied to an IO. And for example, you have an OR gate, you have a B and C as an output. Now you want to test this NOR gate, you need to have this truth table, right? And this truth table, when you have to test it, this has to be converted into an electrical value. So if you want to, and that value is given generated by test set. Say you're either giving a 0 volt or you're giving 1.8 volt. For example, assume your logic 1 is a 1.1 volt within the whatever VIH range. So you're going to apply the tested applies it, and now the output, you need to compare the output. So for that, you have to tell the tester, okay, when I apply this signal, when I apply AB01, my output will be 0, right? So you need to give an input to the tester telling that, okay, at this particular cycle, the tester is highly cyclized equipment, and in this particular cycle, I'm applying, I'm expecting 0. You need to mention that, and then whatever signal coming out of tested, it is compared with the 0 volt, and if it is matching, it is a pass, and if it's not matching, it fails, right? And same thing when it's 1, you're actually comparing against a 1, which is a 1.8 volt coming out of the tester. So when it comes to a tester tested, it's all in the electrical parameters. Okay, eventually everything has to be converted into analog signals. So, and to test your chip, you need to construct a complete vector for each of the test. The simplest form I put was on NOR gate, but you have a complex microprocessors, you have a complex compute machines, which is not a like few signals, right? Your signals could be, your IOs could be 700, 800,000 of signals. So it's not easy. So there are automated tools. The EDA vendors, the who provided the tools, the could be a Tetamax, could be a Tessent, or could be a Pascan, like the various other tools which generates the patterns. So typically when the testing happens, there are two set of patterns which are really used. One is a DFT, designed for test, the scan ATPG patterns, which is a significant part of it in the testing. And there could be other category which is a functional test, where a simple system Verilog VHDL is converted into binary, and then binary to a pattern, test pattern, hex code into a test pattern. So eventually all your test, be it ATPG or DFT, gets converted into a cycle-edged format, which I mentioned over here. Say you have a cycle 1, this is reset clock, like I just picked a few example. So here 1 means you're actually driving a 1.8 volt, 0 means you're driving a 0 volt, and X is where I don't care, right? So whatever the value is puts the chip IO into high G state. Then you have H is like where I want to compare for a high voltage, so compare for 1.8 volt, compare L is compare for 1.0 volt. So each of your data is converted into a cyclized vector, which gets applied to a tester in the analog form, or the tester that converts into analog form and applies to that. So this is a pattern content and development. So this is one of the significant activity, because entire testing, test quality depends on these patterns. If a pattern goes wrong, you are going to end up in testing a wrong thing, and then you may not really have a good result. So it's one of the key activity. And you have various type of patterns like scan ATPG, M based, functional, fuse, many type of the patterns. Okay. Now manufacturing testing, it has a various stages of manufacturing testing. So the wafer coming in, there's a sort test, and typically the sort test may happen at the various timing conditions. So if you today you open a data sheet for any of the IC which you're using in your lab, in the data sheet will have an operating voltage. So it could be minus 40 to plus 110, right? Or it can be like say 0 degree temperature to 80 degree temperature. So now your testing happens according to that, like whatever is the data sheet conditions, it will be tested that. So it's a cold is like whatever is a cold spec, whether it's a 0 or minus 30, minus 40, and then there's a hot which has to be like, which will be like a 110, 80, 90, whatever the spec. So every chip which comes out is going to be tested at the sort, that's at the die level, then at the package level, and at the spec frequency, spec temperature, and same thing, it will be tested at the spec frequency. So your data sheet says this IC works at this frequency, 500 megahertz. Your every part which comes is going to be tested at 500 megahertz, and then it's also going to have the voltage conditions. So if the data sheet says your operating voltage is 0.75 volt to 1 volt, so it's going to be tested at 0.75 volt and also at 1 volt with maybe some test margins, right? So every part will go through that. And after that, once the assembly is done, package parts are done, there will be a qual test, which is a high voltage stress test or like a burn-in test. And once that is done, the part is qualified post burn-in, and that will again go into the um, PPV or a system test, what is told, and then the finish, once it is ready, once it passes, the chip passes all these tests, it will be sent to the customer. Okay. And what are the types of test is done? The first and foremost test which is done on a silicon is a open short test. There's a connectivity test. So this test makes sure that connection from tester board to the that IO pins is good. And also on the it also tests the IO conditions. IO pins are able to connect to the next bus plop inside the SoC, inside the chip, right? And what's done over here is like typically in an open short test, a small voltage is applied, maybe 30 millivolt kind of voltage. A small voltage is applied, and the current drawn by each of the circuit, each of the IO is measured. So if there is a open, then there won't be any current flowing, and if there's a short, then you will see very high current flowing. So, and there will be a spec like what's the right thing to be set. So open and short connectivity is done either the applying a small voltage measuring current or forcing a small current and measuring voltage, right? And the other critical test is a leakage test, which is done on the chip. So it's making sure that leakage on all the IOs and the circuit is not very high. It's like, because if you're not putting the chip into operating condition, it is supposed to be in a dry state most of the IOs and or the default values. And third one is a boundary scan. So this is the, now you have done a open and short, but now you need to make sure that your IO pins integrity. So what it means is the pad, from the pad of your chip, uh, the first flop connection is good, and all the IOs you are able to exercise, they're able to toggle, the IOs are not stuck. Because you can have functional test inside, but if your IO is not working, no signal will go inside the chip. Okay, for example, your reset pad is stuck or it's not working, then your chip will never come out of the reset. So the very basic thing, the first thing which has to happen is all the IOs integrity. All IOs are working, they're able to transmit signals inside and outside. And boundary scan is used for that. And how boundary scan is created? A boundary scan is a pattern, and which is a typically it's an ATPG kind of pattern, or it's a boundary scan pattern which is generated, and it will connect all the IOs. It will shift the values on IOs, and it will use one of the IO as an input, and then it will shift out the values on all IOs, and you will start comparing those IOs. And the second part is you will read all the values from IOs, each of the IOs, and then you will shift out on one IO. So that way you will do both input mode and output mode. So every pad can do operate in the input and output. And boundary scan is typically done, testing is done. IO pins integrity is always done with the boundary scan testing and boundary scan patterns. Right. The next critical thing, which is a very high coverage part, is a scan ATPG testing. The stucket ATPG, transition ATPG, part delay, small delay. So I'm sure you would have studied some of these things in the part of DFT. And so there are various type of scan testing. And similarly for the array memory testing. So memory testing, there are various algorithms, March 13, March, and then you have many other type of each organization will have their own custom algorithms. And these algorithms mainly depends on the memory type, right? And the testing will be different for RAM, ROM, flash, EEPROM, and what other testing you will do will be different. And that's the other critical testing. And you will also do memory retention up to what voltage your memory operates, right? And the functional tests validate critical functionality. Then you will also do the DC parameters, VIL, VIH, VOL, VOH. All of these parameters you will measure on each of the IOs. Setup and hold time measured on every interface. You have an SPI, you have seen SPI timing diagram, and you need to make sure that if every chip which you are sending out meets the SPI timing diagram, the SPI clocks, CMOS, SOMI, all the timing. Right. So that those parameters are measured. Then the performance testing happens with the frequency, whether you meet the right frequency, you meet the voltage, minimal voltage needed for operations, and the other key thing is the power. So the depends on the application where you're using. Say you are using a mobile, you are designing a mobile SoC, uh, mobile chip, then power is the most critical thing, because your chip needs to operate like days together in the standby state, or even operating how much time you can use it for talk time, right? So based on that, the power goals, and those goals have to be met. And also IDDQ, which is a leakage measurement to ensure the quality of the things. And apart from that, yield and diagnostic. So say first one, I will talk about memory repair by the Bazer. Bayer is a built-in repair, and Bazer is a built-in self repair, right? So what happens on a thing is, when you're manufacturing your chip, maybe there are few things like you manufacture a chip, and maybe some memory locations get stuck or they fail. So you have a memory of 1 meg, and out of that, maybe one address does not pass. Now, and in memory is more having more prone to the this kind of failures, contamination during process. Now, if your memory fails, say you have 1 meg of memory in your chip, you made much more. Say one of the memory in your chip, which is 1 meg, even say one location fails, you have to throw that chip. You won't be able to use it. So it's going to be significant loss, right? To avoid that, to recover that loss, uh, typically there is a provision given to do a memory repair. So what happens is, if you have one location fails, one address location of the memory fails, then you will have a few dummy location or a repairable locations which is kept as a what you call extra locations for you, which are not mapped. And now say your particular location, for example, say 0x001 location failed, you will do this Baira and Bizer. So what it does is it calculates which location failed, and then it will map it to what repair capability what you have. So it will remap that empty location, reserved location, to this particular location of 001. Okay, so what happens now, next time when you test it, when you reset the chip after repair, is a fuse blown and the fuse is red. So instead of 001 location, it will go to this new location which is mapped. So even though a location which was failing in the memory, now you have recovered it with a repair. And for that, typically the Bizer is used, built-in self-repair. There are various other methods to do it also, like I'm talking about latest one in the industry, Bera and Bizer, where you calculate and repair it. Right. And the memory diagnostic and failure analysis. So when you have something failing, you need to do analysis done, and then you'll diagnostic. Yeah. We'll talk about switching to quality testing. So, okay. So why quality testing is needed, right? So you need to make sure that whenever your chip is put on a your mobile or anywhere, whichever is application, it could be IoT application, on the board, it won't fail, right? And it will come for its lifetime what it promised. So what happens typically is, like, the silicon is prone to break when you stress on it, right? So when you're actually putting it on a board, what may happen is it may go bad in within a first week, right, within the first few hours of operation. So now, to avoid that, what we do, there's a lot of quality testing which is done. So one of that is a burn-in, right? In case of burn-in, what you do is, I think this is called as a bathtub curve. I'll just walk over this first before I go to burn-in. So in the silicon, what happens is, reliability is, in the initial few hours, it may break, right? It may fail. And if there's a defect, or if there's a gate width issue, or a contamination, or some test escape, or some marginality issues, it may fail in this window. And this is called as the infant mortality of the silicon, right? And now, say once you cross this point, it's going to say, if you buy your electronic equipment, if it works from the first few days, and it's highly likely it's going to work for next set of timeline which is expected, say next 2 years, the lifetime of the product is 2 years or 3 years, 4 years, it will work in that window seamlessly. And you will see again a failure rate here, which is a wear out, which is a routine aging factor of the silicon, right? And it depends on the application, it depends on the what is used, and could be 5 years, 10 years, 15 years, like 5 to 10 years. Now what happens is you really cannot do anything for this aging factor. That's the only time when you have to replace it. But definitely you don't want to see your electronic equipment to fail in this window within a 1 year, or within a 1 week, within 1 hour of you putting it in the phone or putting it in your electronic equipment, right? So this is called as the infant mortality in the silicon. And you will do a stress testing. There's a stress testing is done to ensure that the failure does not occur in this window. And burn-in is one of that kind of testing. In a burn-in testing, what you do is like you put the this silicon, the SOCs, into a burn-in oven, which could be 100-degree temperature or 125-degree temperature or more, and for prolongated time. So it could be like a day, 24 hours, 5 hours, 72 hours, based on the type of application and the process defects, all of that. There's a calculator which tells you like, okay, you want this kind of DPPM and this kind of process, you should should bake your chip for this much hours. So for example, you will put like one of the chip, like you say you put 72 hours in 125-degree centigrade, and then you take that out and you will test it, and if it passes, you ship it to customer. So what you're doing in that process, by stressing it to a very high temperature and the voltage, even voltage is going to be elevated than the operating voltage, you are actually pruning out any of those infant mortalities and on the silicon, okay, and which are very marginalities, and you take that out, and then you ship the parts, so that you are already in within your lab or test house, this window is already covered, and you are going to see a part on the market which is already out of this infant model, or like in the curve, which is active region, right? So that is on the quality testing. And high voltage test and extended life, and there's lot more test which is uh, used. Okay. Now, circuit marginality validation. So this is other thing, like where you have a speed pass, or you have to make sure that your circuit marginalities and the failure rate, like thing like, and and you meet all the voltage requirement, temperature requirement, frequency requirements. This one of the type of the testing. I'll talk about system validation. This is the other thing. The scope of system validation is to perform platform level and bench validation. So now you already done a manufacturing testing with ADPG, DFT, or functional test that has proved the manufacturing defects are screened out. Now still you need to make sure that your design spec is met on the silicon, right? And functionally it meets. So the ATPG will tell you like you have met manufacturing issues, you have screened out, but you have to make sure that you have met the functionalities, you have met the electrical parameters, AC DC parameters. So that is done on a system validation. So system validation is nothing but a pure FPGA board connected to a CPU. You are actually going to run the complete validation suite, functional validation suite, which is written in a C with system verilog, any type of thing. And system validation is done on a handful of parts, not on every part. Like it's just to make sure that your parts are correlating with the design. And typically what happens is we do a system correlation on few parts of various spectrum of the process. Say when you do a process, you want to do a process which is ideal, right? But always what happens is time to time that may spread across, like you will have a variations in your process. So typically it's called as sigma variations, and that sigma variation could be like 7% like 1 sigma, 14% 2 sigma, like that. And typically we test 3 sigma variation, which is called as a slow and fast material. So we create a spectrum and verify it, sample parts on system validation across the spectrum. We create a slow parts, we create a fast parts, we create a nominal parts, and test it across temperature, voltage, and make sure that the functionality meets with the design, and then we stop it, like is after correlation is done. Right. And the other thing is a platform validation. So this is a runs on a platform running actual end user application and targeted software. So this is like, say, even after doing all of the testing, it's not guaranteed that you will meet a DPPM. So what we do is like, okay, there's a every part which comes will go through some amount of system validation. Some amount is the test content which is running on a platform validation is same as a system validation, and it will be running like same content and making sure that uh, the whatever not covered in ATPG or whatever not covered in the structural testing is covered in the platform with the software part or software code running, and typically a boot test and many other tests which gets tested. So this is on now I'm coming to, so that much gives a very high level. I've not gone any of the topic because each of the topic needs significant amount of time to go in detail. And now coming to a skill set, like what are the things needed, right? What are the things needed for the uh, mm, skill set to in to work on these domains, like. So first and foremost thing is, I think, a basic electronic knowledge like voltage, current, resistors. You should be very thorough with all of them, and memory devices, circuit, all the photolithography, etching, and building these skills can help you to build an expertise. I think whatever the first bullet which I put, like silicon manufacturing, this critical skill set, irrespective of you work on post silicon or not, all these 3 plus 3 6 7 bullets which I put, this knowledge is very important if you are going to work on VLSI. Okay, it doesn't matter whether you're in a design, validation, post silicon. So they are the basic thing which you will have to live with rest of your life, right? And if you're working on test hardware design, then there's a board PCB design knowledge, a PCB board design knowledge. There enough material to read, and then you can and test content generation. The key thing is like, if you want to work on a test content generation, you have to have a good knowledge on the DFT and scan ATPG, MBIST array test development, and functional validation knowledge, C, SV test development, and the solving skills, debug skills. Because when it comes to silicon, the debug is really challenging. I've done a lot of silicon debug, which is a dead on arrival, like where you don't see any activity happening in your chip, and then you have to spend weeks together in debugging it because you really cannot see what is happening inside the chip, and you should have architecture knowledge and the debug skills to go and root cause to a particular area where it's failing. So that knowledge. So when I say these skills are needed, don't get confused with the tools flow knowledge. That's one part of it, the tools usage. But what is needed is the architecture or the understanding of the domain. That's a very important part, right? And system validation, again, here the C++, the people who, the companies which code in C, there are some companies in the system verilog, and hardware board testing knowledge, hardware device skills here. And about that, I will talk about soft skills, right? uh, there was a session I saw on the soft skills, but I'll just briefly summarize. The key is a communication skill, right? And you have to be crisp and clear in your communication, and you should be prioritizing tasks and how to say no. And you should have a very good organization skills where you can work with a team and you can call out the risk, you can understand the things. And what makes a difference is a proactive problem solving and independent ownership. And typically when I've been going for campus recruitment and hiring fresh college graduates into my team for last 15 years. And what typically people expect is there's a problem, they expect a solution coming given by someone else. Or like, see, when you're studying in the college, you have a textbook where you can read and you have a answer for every question. But when you start working, when you have to debug a silicon, there's no FAQ, there's no question book, or there's no notes from anybody, and nobody's going to teach you, right? And you need to build that solving skill and independently own. See, there's something which you're not understanding and you're running out of time, you have to call it out. I'm not understanding this, I need help here. You have to go and talk to your manager in the corporation where you're working. And then you will get a required help. Then if required, you have to call a proactively call a meeting with all your team members. And many times it happens, people just sit on it. You just call a meeting with all your rest of your team and put a problem. I have this problem and I don't know how to do it further. I need your help. Right. And that one, and openness for feedback. You have to have a, I keep telling that feedbacks keep coming if you don't act on them, but not the opportunities. And many times opportunities come only once, right? So you have to grab it when it comes. So you need to be open for your receiving feedback. You need to act on them. And feedback is not about like what you think, is about what others think about you, right? It's a perception of you from the others views. So it's a good thing. So these are the few soft skills. I think very much that's what I had in our session. And I would like to end my thing with another statement from Andy Grove. The how well we communicate is determined not by how well we say things, but how well we are understood. So the key of communication is not how you say it, it's about how we are able to make other person understand. That's the key part. And uh, I work on it. That's a very important thing, skill, uh, on the soft skill which is needed. Okay. So I'm just ending the session and opening up for any questions.
Shankar, yeah, thank you. Right, so there are some few questions. I'll start going through them. Right, and okay, could you give some reference link and a book for testing of VLSI?
Yes, I can share it with offline. Right now I don't have it with me. Intentionally I thought of putting that, but initially I didn't put it because I didn't want to show it as a marketing for any of the books or any of the publishing. But if you do a Google, you will find a lot of books on the VLSI, right, and in bookshop. And I can also share it offline. I don't have it handy.
Yeah, next question, power aware test vector compression decompression scan architectures. Is there a research area still good to take up?
Exactly, yes, it is. It's very good question and very big thing. Okay, so today power is one of the very critical thing. I'll tell you one of my experiences. So when you're functionally testing a chip, you're only exercising one part of the logic. Say you're trying to do a PCI data transfer, only part of the SOC will be exercised. But when you're going for a scan testing, your entire scan network or your every flop in the design is going to toggle, which is going to create very huge power, right? And now each of this tester has a limitation on what power it can supply, right? It could be certain number of amount of amps which it can supply. So today the power consumption on while testing, which is not a real silicon issue but it's a testing issue, and also the power consumption and the IR drop, right? The IR issues, like the where your localized IR issues or global IR issues, they are the very critical thing. And every organization, I work not the organization, but I know like pretty much everyone is struggling with the power hungry chips, because we are putting more and more. Now we are talking about billions of gates in an SoC, right? And we are talking about like 500 to 1000 square SoCs. So it's not a small thing. So it's still a very big area, and I would say still kind of open. Like it's not something I'm not saturated. So there's a huge opportunity for further optimization and the power aware patterns, all of that. And because once you go for a power aware pattern, your pattern inflation happens. And again, when the power pattern inflation happens, everything is tied to cost, right? If your test time, say you have a test time of 10 seconds and it becomes 15 seconds, you actually end up paying more for testing. So it increases your cost and profit margins decreases. So it's a very important area to optimize.
Okay, if you tell our manager that I don't know how to solve, will he get the impression that I'm not capable and will it reflect in my appraisal?
No. See, when you call it out that I don't know how to solve it, right? That makes a lot of difference when you call it out. Say you have a goal, for example, you have a goal which you have to complete by 30th of October, and 29th you go and say, I don't know how to do it. And that's a kind of thing not going to be received well. But say you know that 30th October it has to be solved and you need 10 days for that work, and you go and call it out on, say, well in a time that I don't know this, I need this help, right? And it's going to be seen as a positive. So what will be highly rewarded is your ownership, right, to solve it. It's not that you know everything. None of us will know everything. Okay, each one of us, and especially when you come to the industry, it will be, work is fragmented in so many pieces, right? There's, it's like a puzzle. Each one will be having their piece of the puzzle. Unless everyone comes together, picture is not going to happen. So you're not going to it's not going to be seen as negative if you go and say I don't know, right? And if you ask for the help at the right time, yeah, it's a positive, by the way, and as long as you complete the work. Like I was telling, like, best thing is that many times we do it like we call the team and say this is a problem and I don't know what to do, I'm stuck here, and we prepare the material and flash it, this is what we have done, A B C D, and now we're stuck, right? And then we do a brainstorming for hours together to what next step. So with the right expertise in the room. So that's the kind of thing. So it's not seen as a negative, it's a positive.
Yeah, pre-silicon or post-silicon validation, which is more challenging?
Okay, they're very two different things. Okay, so now me coming from I worked in pre-silicon and post-silicon both. Okay, I won't say which is more challenging, because both pre-silicon has its own way. You have to meet the coverage goal, you have to make sure that your code coverage, functional coverage, toggle coverage, all of them meet. And when you come to post-silicon, it's very different ball game. Now when you come to post silicon validation, typically you don't have access to all the internal signals, and all you have to get it through debug hooks in the through JTAG or debug hooks in the present in the chip, and you need lot of architecture knowledge and logical thinking to debug the post silicon. And say your chip is not powering up, right? Your chip is not coming out of reset, and you should know which signal to look for, right? So it's a debug wise, post silicon is very challenging, and it will be really making you a lot of things. Like I will tell you, I had couple of times like where weeks together without having any clue why chip is not working, and that's a kind of thing, like that's a post silicon life. And pre silicon you won't see that. Like pre silicon, okay, it's failing, you know, you have to put a dump and go and look at the signals, right? So it's a very different challenge.
Okay. Another question. Suggest some good project in the testing domain.
Suggest some
Good projects in the testing domain.
So I didn't understand the question. Yes, asking
We
for
want
that.
some project. We want to learn testing. So what are a project you should do to learn testing better?
Okay, I would say like there's nothing called a project in testing, because you need to have a design to test it, right? So it's not something you is the testing is not an isolated activity. Maybe your design can happen, you can start doing some design, but for testing there has to be a DUT. Okay, so a design, and it's going to be an extension of the design for testing. And if you want to learn, go in deep in testing and learn, is like one of the thing is you have to understand the DFT in detail, right? And then you need to understand the functional validation in detail, so that will give you more insight, more deep knowledge on the domain. And testing is something, it's not something isolated one, no.
Okay, thank you. Yeah, there's another interesting question. If you have a skill set and if the class 12 marks is really matter to get a job as a fresher,
What is
if you have the right skill set, but in 12th standard, his marks are not very great. So will it
okay,
matter? Yeah.
Okay, here's the thing. When I go for an interview, what I look for, right? When I go for an interview, if your skill sets are good, it will be like positive, right? But I still look at the marks. It at least tells you how hardworking you are and how much you scored. But it really does not mean that just because of you have a good mark and you're going to get a job. No. So and now on the contrary, I have seen people who are even having a score of 60, but who are really have done good. They have good analytical skills, problem solving skills, and they do really good on the interview. So they get selected. So now whether the class 10 score matters, I would say may not, but does not mean that you should score less, because your score is a gateway to get to an interview, but that's not the deciding factor for your job.
Yeah, one last question. There are other questions, probably that's a separate webinar topic. Somebody's asking for experience on when the silicon was dead and how it was root caused. That's a separate webinar topic, so let's not open up here, right?
Okay.
It's fine.
Yeah, I have multiple things, and it's a very
Yeah,
wide
you and I
area.
have a lot of
Yeah,
stories to tell. Yeah, we'll do it
correct.
separately. Right?
Yes, yes.
Right? And yeah, so what are the skill required by MTech VLSI design student to get an internship in a chip tester company? What kind of skills he need? I think you
See,
addressed at the beginning. Yeah,
correct. I addressed it. See, the few things I want to say is one is many of this testing will be quite custom skills, right? Each company will have its own. But the few things which you need to build is you should have very good knowledge on the VLSI, the flow CMOS and architecture design. Second thing is have a good knowledge on DFT that will help, right? And also the functional validation, SV coding, C coding, those kind of thing. That will fetch you a much faster. This one, those are the skill set which is needed. I won't say fetch you anything. They are the skill set needed for the job. And the tester companies, even when we go for hiring for the post silicon testing, we look for those skills. If somebody with because I don't expect a college graduate coming out, be it MTech or BTech, knowing the how tester works, right? Because you don't have access to that. Each of the testers cost in the millions of dollars. Okay, so each cost. I worked on a tester which is like $3 to $4 million. So you won't even get to touch them unless you start working on them. So you won't have those skills. So what skills needed to go over that? The ones which we look forward will be like DFT and your analytical knowledge, your CMOS architecture, and how much you know on the all your terminologies, setup timing, the timing, and the VIL, VIH, all electrical parameters, the DFT and the SV coding. And also some amount of scripting. Whether you go to any domain, the scripting is one of the most important thing. At least you should know one scripting language. That helps.
Thanks, Shankar. I think yeah, end of the question. Madhu, over to you.
Hey, thanks, Hari.
Yep.
Yeah.
Thank you so much, Shankar, for taking time out and actually giving your inputs and such valuable feedback to students. We hope they can, they gain knowledge out of this. And thank you to all the attendees. We just want to share the next session we have coming up on 14th of October, which is product development cycle of an SOC by Mr. Uday Joshi. He's the CTO of Intratech. Do attend and do fill up the feedback, and we'll see you in the next session. Thank you again, Mr. Shankar, and thank you again, Mr. Balasubramanian, for taking time.
Yeah. Thanks, Madhu. Thanks, everyone. Hey, to all the attendees, I would say don't miss Uday's session. Uday was my manager. I learned a lot from him, and definitely you will have much good learning with him.
Thank you so much.
Thank you.